So today we are talking about the speed of sound and kind of just continuing with a little bit of an introduction to sound. The last class period I had you fill out this document. I just got some of the answers here. I put my answers in red. So a sound wave travels as a mechanical wave. And a mechanical wave needs to have a medium for it to travel through. Not only is a sound wave a mechanical wave, but it's also a compressional wave or a longitudinal wave, which means it travels with compressions and rarefactions. So the purpose today is to talk a little bit about the speed of sound in air. One of the things that you may notice is that the speed of sound and the speed of light are different, which is why, as part of today's lesson, we're going to talk about how you can tell how far away a thunderstorm is. We're going to clear that up because I know your parents have probably told you some kind of myth like it's 1 mile for every 1 second or something. We're going to get that nailed down today. And also that, just the speed of sound and the speed of light are different. So the first thing you need to understand about the speed of sound, and this is kind of like I said, the second time you've seen this, is that sound travels differently through different materials. It's a mechanical wave. It has to have different materials, or a material to travel through. Depending on the material, it's going to travel at different speeds. And what we've noticed in the past is that solid materials transmit sound really well, and things like gases do not transmit sound as well. But if you notice, there's also something with temperature here. And it looks like with temperature, the higher the temperature, the faster the sound moves. And that's actually ultimately what today's lesson is about. So what two factors affect the speed of sound? The density of the material and the elastic property of the material. How easily can the atoms of the molecules move and bounce back to where they came from? Are they elastic or not? So if I move down just this little bit further, the higher the temperature, the faster the sound moves, and the lower the temperature, the slower the sound moves. So that's all the further I'm going to use that document a little bit every day. So here's some things. Number one, this is the speed of sound at 0 degrees. That's going to be an important number because we're going to use that in a math formula today. So make sure that you have this piece of information written down. Number two, I just mentioned this. The speed of sound depends on the elasticity and the density of the material. Elasticity means that the atom can bounce, like it moves, and then it comes right back to where it bounced from. Density is just how tightly packed they are together. So these two things, a very elastic and a very dense material, is going to have sound travel the fastest. So because sound and light have two different speeds for how they travel, you'll see the lightning before you hear the thunder. And roughly speaking, if we're in a country that deals with things in kilometers, every 3 seconds means it's 1 kilometer away. So here's a little video for you to watch. Check. All right. (1001), 1002, 1003, 1004, 1005, 1006. 6 seconds. Every 3 seconds is a kilometer, so that would be 2 kilometers away. It's a pretty cool lightning strike. (1001), 1002, 1003, 1004, 1005, 1006, 1007, 1008, 1009, 1010, 1011, 1012, 1013. I got 13. He's doing it in miles right now, just for the record. There's a flash over there. In the second example, he did do it in miles. So if you wanted to do it in miles instead of in kilometers, every 5 seconds is 1 mile. And like I said, for that second flash, I got about 13 or so, so we could probably round that to 15, because I wasn't being really super scientific with like a stopwatch or something. And if you count by 5s, 15 divided by 5, it's about 3 miles away. It's not perfect because you got to remember that the temperature is going to change the speed of sound anyhow. So it's kind of a rough science, but there you go. Every 5 seconds equals a mile. Let's look at that formula for temperature, because here it is. If I want to adjust the speed of sound, because this is 330 at 0 degrees centigrade, if I want to adjust it, this is the formula I'm going to use. For every degree it is away from 0, you're going to add 0.6 meters per second to it. So it travels faster if the air is warmer, and it travels slower if the air is colder. So here's an example problem using that formula. It says, what is the speed of sound if the air is 20 degrees? Well, I know what the speed of sound is. If it's 0, it's 330. But if the air is at 20 degrees, this is how that formula looks. And I know it looks kind of messy here when I first started, but I'm going to take the 330, and the first thing I have to do is I have to figure out what the change in temperature is. So I'm going to take 20 and I'm going to subtract 0 from it, because 0 is what 330 is. So if it's 20 degrees, I'm going to take 20 and minus 0. Well, that's really easy math. That's just 20. But that's the first step, is you have to get the change in temperature. And then once I have that, I'm going to take the 20 times the 0.6, because that's in parentheses. And when I take 20 times 0.6, I got 12. So 330 plus 12 equals 342. The Celsius and the Celsius cancel here, if you're wondering where that Celsius went to. And that's going to be the answer. So let's say I had a different problem. Let's say I had a different problem where the temperature was negative 15 degrees. If it was negative 15 degrees, this would say, negative 15 here. And then this would be negative 15. And negative 15 times 0.6, just one moment, let me get, negative 15 times 0.6 happens to be negative 9. So now if you look at how this kind of plays out, 330 minus 9 is 321. So if it's colder than 0, if it's a negative temperature, you end up moving slower. The speed of sound is going to be slower if it's less than 0, and the speed of sound is going to be faster if it's higher than 0. So the math works out on that. Check it out. There's a couple problems where you have to do just like this, and then there's a couple problems where you have to do it with a positive temperature. So the first two I think are positive temperatures, and the second two are negative temperatures. This is the homework assignment for the day. So here's 15, here's 40, and then see the next two have negative temperatures. If you need to go back and rewatch that part of the video, you can do that. So just kind of jump back and watch that again. I'm going to show you kind of how you do the last 4 problems of this as well. So let me do another example here. So if I take this formula and do some algebra on it to rearrange it, I would get a formula that looks like this. And basically, instead of trying to figure out what the velocity of the sound would be, this is going to tell me what the temperature is. So the problem that I'd be trying to solve would look like this. What is the temperature that results in the speed of sound if the speed of sound is 342? So if the speed of sound is going to be 342, that's this number right here. So basically all I'd have to do is just take that number and put in my 342 meters per second. Don't forget your units, because units are important. So if I take 342 and minus 330 and then divide by 0.6, it's going to tell me the temperature. So I actually think these problems are a little bit easier mathematically to solve. Let's go ahead and do this one just so you kind of see what the right answer would be. So I got my handy dandy calculator here. I'm going to take 342 and subtract from that 330, hit enter, and then divide by 0.6. And the answer there would be 20 degrees. So the temperature would be 20 degrees Celsius in this particular problem. Again, if this number, if it was colder out, right? So maybe this number here is 250. Maybe it told you in the problem that it's 250. Same problem. It's not. Make sure you punch your numbers in the calculator, right? Subtract your 330. And in this case, this is going to be a negative number. So when I divide by 0.6, it just simply means that we're below 0 at this point. Okay? So that's 133 degrees below 0. And that's fine. You can have that for your temperature if that's what it was. For units, the meters per second cancel out, and you're left only with degrees Celsius. All right, that should help you with your homework.